In this part, we want to learn how to solve a linear programming model using Excel solver. Solving more complex linear programming problems. So far we have solved very tiny problems that have had only two decision variables. But typical problems, even small typical problems that we face daily or businesses face, have hundreds of variables or thousands or even millions of variables. So past two variables, how can we use the graphical method? We can't really, it would be really hard to, for the three decision variables, we can use a three-dimension space, for example, using a computer to do that. But past three in four dimensions, four decision variable, we can't really use the graphical method to solve an LP problem. So what should we do then? Well, actually, there are mathematical solution techniques, very efficient, that can be used to solve complex LP problems efficiently. An example of that is known as the simplex algorithm, which was which was invented by George B. Danzig. We're going to learn about Danzig a little more. Here's a fun fact. Let's learn about George B. Danzig, the scientist who came up with the simplex algorithm that changed the operation research and its application. George B. Danzig was a mathematician. He was born American mathematician. He was born in 1914 in Portland, Oregon, and he died in 2005. And he lived in California, Stanford. So as a professor of operation research and computer science in Stanford University, he contributed a lot to uh, advancing the science of operation research and specifically linear programming. He actually was the pioneer in linear programming. He's mainly known for his development of the simplex algorithm, um, which still is being used to solve LPs. Also, one fun fact about George B. Dancy, to give you an idea how smart this guy was, in one of his classes at the university, he was late. When he when he got into class, the professor was already solving, assigning actually some problems to students. This is what he thought. So there were problems on the board, the blackboard, that George wrote them down, and he thought that those problems were assignments or homeworks. So after his school, he went home and worked on them and solved the problems and brought back the problems. But the reality was the professor actually was introducing open problems to students. Open problem in mathematics and also other areas are those problems that no one had ever been able to solve them. So George was able to solve two open problems, two mathematical open problems, thinking it was an assignment. They were assignments. All right, so let's use these efficient mathematical methods to solve an LP problem. So here we're going to revisit our first example, which was, if you remember, a toy manufacturing company was producing two types of toys, the space rays and the zappers. X1 here is the model as you see. X1 represent the quantity of production for the space rays and X2 represent the quantity production for the zappers. And also you see the constraint here for the amount of plastic, the limited resources they have, the production time and the total production mix, and also the non-negativity constraint. So we are not going to go through the depths of the theory behind the mathematical approach, such as the linear programming or the intermediate point method. Instead, we're going to use softwares that use these mathematical methods to solve this problem. In this course, we're going to learn how to solve an LP problem using Microsoft Excel. So let's see how should we actually put the input, put a problem into Excel file and how to solve it. To be able to use Excel to solve LP problems, you need to have installed the solver add-ins capability. Okay, so to check whether you have it or not, go to the data tab here, and then on the right side there should be a section which is not here called the analytics tab, and in that analytics tab you have the solver. So there is none here, so I'm going to add it. So I'm going to go to file. This is, by the way, in Windows. For Mac might be a little bit different. So I'm going to go to the options here, and from the options I'm going to go to add-ins, and here manage Excel add-ins. I hit go, and then it's going to go to this windows. Then I'm going to select these solver add-ins. I checked it, and then I hit OK. Now if I go to the data tab, I have the analyze tab here, analyze group, and I have the solver here. So now I can solve linear programming problems using Excel solver. Now let's learn how to solve a linear programming model in Excel. So I have put the model, the linear programming model for example one here, the Galaxy Industries. This is the objective function, maximize the x1 plus 5x2, which is x1 is the dozens of space rays, x2 is the dozens of zappers, and here are the constraints. But Excel does not understand this formulation, so we need to put it in a way that would understand it. That's why I have created this table and setting right here, which is basically going to be the similar. If you want to solve any other problem, you just have to extend it. So here are the decision variable x1 and x2, x1 space rays, x2 zappers, and these blue shaded area. These are the cells. These cells are going to show the objective value, the optimal values for x1 and x2. After you solve the problem using Excel, it's going to print out the optimal values for x1 and x2 here. Then here we have the profit line and the constraint. So to put the profit, you see that there's a column here under x1. These are the column under x1, and these are the column under x2. So here, we're going to put actually the coefficients in this table right here. So let's go ahead and put the objective function here. So the objective function is maximizing 8x1 plus 5x2 profit. So I'm just going to put the values here. Under x1, that's 8x1. So that here I'm going to just put 8. I'm just going to put the coefficient, the numbers here. And for x2 is actually 5. I'm going to put 5 here. How do we write the 8 multiplied by x1 plus 5 multiplied by x2? Now I can do this. 8 multiplied by x1 plus 5 multiplied by x2. So this is one way to do that. But if you have more than 2 variables, it's going to be tedious to just multiply plus multiply plus. So instead we're going to use an Excel function called sum product. Sum product. So sum product, it is going to take the arrays here. So the first array is going to be the coefficient 8 and 5, comma, and then x1 value and x2 value. So what it's going to do is the same. It's going to multiply 8 by x1 plus 5 by x2. And if you have more, it's going to do the same. All right. And here, this is the objective value based on this, based on the value of the decision variables, 8x1 plus 5x2. Now the value of x1 and x2 here is none. That's why it shows the profit of 0. So if I put, for example, 1 here and 2 here, it's going to put a value here, as you see. All right. Next, we're going to put here the constraints here. So let's start with the plastic. It says 2 multiplied by x1 plus 1 multiplied by x2 less than or equal to 1,000. So we see actually 3 parts here. The first part is the left hand side of this inequality. I'm going to put this inequality here, less than equal to, and then here is going to be the left side. So I'm just going to put the coefficients. So 2 multiplied by x1, 1 multiplied by x2. Under x1, that's 2, 2 here, and under x2, 1 here. Okay. And here is actually the setting. So that's 2 multiplied by x1 plus 1 multiplied by x2. Instead of doing this, I'm going to use the sum product again. Sum product. 2 and 1 coefficients, comma, x1 and x2 values. Parenthesis close, enter. So again, because x1 and x2 values, these two are none, that's why it shows a 0 value here. So that's the left hand side here. And then we have inequality here, inequality here, and the right hand side or the parameter is 1,000. I'm going to put it here. 1,000. Okay. So this is our first constraint for plastic. The second constraint is 3x1 plus 4x2 less than equal to 2400. So I'm going to do the same. 3, 4, I'm going to put the coefficient here, 3 and 4. And here I'm going to use the sum product, 3 and 4, comma, x1 and x2 value. Parenthesis close, enter. And here is the symbol, mathematical symbol less than equal to, which doesn't matter here because if you have to put it in Excel, I'm going to show you how to do it in the solver. And here is the right hand side, which is 2400. Okay, so 2400. So we are done with these two constraints. The next constraint is the total production. So that's x1 plus x2. So that's 1 and 1, right? 1 multiply x1, 1 multiply x2. And then here we have less than equality. And here we have, again, sum product. 1 multiplied by x1 plus 1 multiplied by x2. So instead I'm going to use the sum product. The coefficient, the first array, and comma, x1 and x2 values, parenthesis close, enter. And then here we're going to go to the right hand side or the parameters here, which is 700. So I'm going to put 700 here. And then the last constraint, that's 1 multiplied by x1 minus 1 multiplied by x2. So instead you can read this as this. 1 multiplied by x1 plus negative 1 multiplied by x2. So this is how I'm going to put this. 1, negative 1. And here is going to again be sum product. Sum product 1 and negative 1, comma, x1 and x2 values, parenthesis close, enter. And here is less than equal to. And here is the right hand side value, which is 350. Okay. And then we have the non-negativity constraint. We don't need to put the non-negativity constraint here. We can put it on the solver. Okay. So we are done modeling the problem in Excel. Next is how to solve it. Now we're going to go to the data and the solver that we installed. So we have it here. It opens this window. Here is the set objective. And this is where you have to set the objective. This is the objective, the profit that we have, which is 8 multiplied by x1 plus 5 multiplied by x2, or the sum product here. So that's D6. All right. This is the problem minimization or maximization. It's maximization. All right. By changing variable, this is the decision variable here. So these are the two decision variables, x1 and x2. And then here is the constraint. I'm going to add the constraint here. Add constraint. Cell reference is these sum products that we had. For the plastic is here. here is less than equal to. So as you see here, these are symbolic. We didn't actually use this in the solver. This is just for showing you that what are the constraints here, less than equal to, and then the constraint is here, or the parameter or limit. Then we add it. Next one is the production time. Is here less than equal to, the constraint is 2400 or the limit is 2400. Okay. We actually need to add one more. We have the total less than equal to 700. Add mix this less than equal to 350, and that was the last one. I hit OK. So now we have all the constraints: 1, 2, 3, and 4. 1, 2, 3, and 4. So we have all the constraints here. Next is make unconstrained variable non-negative. You don't have to worry about this. The solving method is, I'm going to use the simplex LP, linear programming. So use the simplex LP and then hit solve. All right, it says solver found a solution. All constraints and optimality conditions are satisfied, and keeps solver solution, reports, return to solver. Don't care about this now. Solver found a solution. All constraint optimality conditions are satisfied, and I hit OK here, and here we go. So what changed here is these two values, as you see. Excel found this solved this problem to the optimality and found the optimal values of x1 and x2, and also the optimal objective value. So if the Galaxy Industries produces 320 dozens of space rays and 360 dozens of zappers, it's going to be the maximum profit possible that they can make, and that's $4,360. So this problem is solved. In the solver menu or window, after you have put your decision variables and your objective function and your constraints, and you hit the solve button, there are two things that might happen. You might actually get a solution, the optimal solution, which the solver shows the reports of the optimal solution. That means it shows you the optimal solution value and the decision variables at optimal solution. Or it would give you an error if there is a problem in the model that you have to resolve it. The Excel solver, when you use it to solve a linear programming model, can actually produce for you what is called as answer report. In this report that you see, this is based on the example 1 that we solved, it gives you the total profit here, the optimal value, and also the decision variables at optimality. So this is for x1, a space rays, the amount of space rays produced, and the amount of the zappers produced as optimality. And also it tells you about the state of the constraints at optimality. So this is constraints, for example, the total plastic constraints, which is less than equality. This is a binding constraint, so there is zero slack. So for less than equality, we have either a slack or we have binding, and for greater than equality, we have either surplus or we have binding constraint again. So here, the plastic constraint, it is a binding constraint. Okay? So this is important because it tells you that if you want to improve or increase your profit, you have to increase the plastic amount or plastic resources. Also, the second constraint, the production time total, this is also a binding constraint. This means that, okay, if you want to, again, improve your profit, increase your profit at optimality, you need to increase the resources that you have for the production time. On the other hand, if you look here, you're going to see that the total constraint here is a non-binding constraint. nor is the mix total. That's also a non-binding constraint. So increasing these resources would not improve the profit, increase the profit. So let's now see how to actually produce this table from the Excel solver. So this is our problem here, our Galaxy Industry problem, the table that we had before. We go to data and solver, and we get all this model that we have imported here, and then we're gonna hit solve. So it's gonna solve the problem. Then we're gonna ask it to produce the answer report, and then I hit OK. And if you look here, it's going to generate a tab, Excel tab here. And this is the tab that we went through. So it shows the optimal objective value, the profit here, 4,360, the decision variables at optimality, the dozens of space trays and dozens of zappers, and also about the constraint, whether they are non-binding or binding constraints. Let's now solve example 2 that we modeled before. You can see the model here using Excel solver. So here is I have set up the setting for the second example, the microcomputers here. Here's the model. We need to put the model in Excel so that Excel can solve it. So we have two decision variable x1 and x2, the quantity for type 1 and type 2. The objective function is to maximize the profit for each type 1 computer. They make $60, and for each type 2 they make $50. And these are the constraints for the assembly, inspection, and the storage. So let's go ahead here. This is our decision variable. X1 type 1 computer, X2 is type 2 computers. And here are the profit coefficients for X1 and X2. So for X1, it's $60. The coefficient is $60. And for X2, the coefficient is $50 in the objective function here. So here, we need to make this objective function. That's 60 multiplied x1 plus 50 multiplied by x2. That's 60 multiplied by this cell plus 50 multiplied by this cell. But instead of that, I'm going to use the sum product. So sum product, 60 as 50, the coefficients, and comma, x1 and x2 values. Parenthesis close, enter. Right now it's 0 because x1 and x2 values are none here. So the same thing for the constraints here. So in the constraint, we're going to put the coefficients of x1 in this column, the coefficient of x2 in this column. For example, for the assembly, the coefficient of x1 is 4. So I'm going to put 4 here. The coefficient of x2 is 10. So I'm going to put 10 here. The right-hand side is 100 hours. So I'm going to put 100 hours here. And here we're going to make this function 4 multiplied x1 plus 10 multiplied by x2. That's 4 multiplied by this cell plus 10 multiplied by this cell. I'm going to use the sum product 4 and 10, comma, these two cells, parenthesis close, enter. Okay. For the inspection, 2 is the coefficient for x1 and 1 is the coefficient for x2. So that's 2 and 1. And the right hand side is 22 hours. And this is, we're going to use the sum product again, sum product 2 and 1, the coefficients, and these two cells for the variables. Parenthesis close, enter. For the last constraint, the storage, the coefficient for x1 and x2 are 3. So this is 3 for x1, 3 for x2, and the right hand side is 39 cubic feet, as you see here. And here we're going to use the sum product 3 and 3, the coefficients, comma, x1 and x2 values, parenthesis close, enter. Right. So now our model is ready to be solved using the solver. I open up the solver. Here is the set the objective value. So this is going to be this value here. Right now it's 0. So we want this cell to maximize. right? Because our problem is a maximization problem, maximize this function. By changing, this is the value decision variables, these two cells, our decision variables. And then here we're going to add the constraints. The first constraints here is for the assembly, less than, and this is the right hand side, add. The next constraint is for the inspection, less than equal to, the right hand side is 22 hours, add. We had the last one is storage. This side, the left hand side, should be less than equal to the right hand side constraint limit, which is 39. Since we don't have any other constraint, I'm going to hit the OK button. And it's going to give us back to this window here. Now we check this, make the constraints variable non-negative. This is the non-negative constraints here, as you see. And we want to solve it using the simplex linear programming. So hit solve, and it says solver found a solution. All constraints and optimality considered are satisfied here. So you can hit OK. And as you see here, it actually computed these two variables. So this is the 60 is the optimal value of type 1 computers, and 50 is the optimal value of the type 2 computers. So it means that the company should produce 60 of computer type 1 and 50 of computer type 2, and they're going to make a total of $740. So you can also actually ask it to produce um, the answer report here. So this is the answer report it produces here. So the profit is 740. The quantity type is 9 and 4. And these are the constraints. The storage total is the binding. The assembly is not non-binding, and the inspection also is binding here. So if we go to our example, we're going to see that this is the case.